So today we're going to continue learning about t-tests. Previously we saw the one sample t-test, and that meant we had one mean to compare to a null. Now we need to learn about when we have two means. So a comparison between two groups is very common design in biology. Oftentimes we're looking at a comparison between treatment and control, or between two treatments, or maybe even a before and after. So there are two other basic designs for t-tests in addition to the one sample t-test. That's paired samples, also called dependent samples, and independent samples, both types of t-tests. And in this graphic, you can see the difference between paired versus independent. In the independent, you can see that every measurement we make, so if every square represented an experimental unit here, that we have two groups. They're not linked in any way. Paired, on the other hand, means that we have an experimental unit that is often measured twice. So, as I said, same individual is measured twice is the most common for a paired design, before and after, a right hand and left hand. But in this case, you have one experimental unit that is being measured maybe before and then after, say before a drug treatment, after a drug treatment. Okay. Also, you might use a paired design when you're blocking together experimental units, or when the observations are in another way linked. And often we see this in identical twin studies where you're testing both twins because they're genetically identical, but you pair the design because they are very much linked. Okay, I'm just throwing this slide back up here again because we don't want to forget the steps that we use in a general statistical null hypothesis procedure, and that's going to stay the same for our other t-tests. So for any t-test, we're getting a t, or a test statistic, that takes some statistic, and for us it's going to be mean, and we're going to minus some hypothesized value, and it's going to be over the estimated standard error of the statistic. So I like to think of this as the numerator as being the signal over the noise. And for a one sample t-test, what we saw is we had some sample mean, and we minused the null hypothesized value, and we divided by the standard error of that sample mean. And remember, we only measured one sample, one set of experimental units that we only measured once. So the paired looks similar, but a little bit different. In this case, our D is going to represent the mean of, say, before minus the mean of after, and so we're going to get a mean difference. That's what that bar over the D means. It will be a mean difference. And then it will minus some null hypothesized value. In many cases for this it's 0, because we would expect no difference before or after under the null, but it could be something different, but we will almost always see 0 as our null value. Then we're going to see that we can calculate not only a mean difference, so we've taken a set of experimental units, we've measured them twice, we get two values, we subtract one from the other, we get that mean difference, which means we can calculate a standard deviation of that mean data, and then of course we can then calculate a standard error of that difference. Okay, again, paired t-test, again, they are linked somehow. The experimental units are either dependent on each other, or they're the same experimental unit with two measurements coming from them, so they are not independent from each other. Okay? And as I said, under the null there is no difference in before and after, so oftentimes we'll see that null value being 0. We do have the same assumptions as a one sample t-test. And as a matter of fact, that our test statistic is very similar to it, other than using a difference. We have to have independence of observations, random samples, and we need to have normality of our data. And you can do your Anderson-Darling test for normality on your difference data set. So once you calculate that difference. Here's an example in your book, a red-winged blackbird and testosterone and antibody production. So in many species, the males with the highest testosterone levels attracts the most mates, can contribute to their coloring or vocalizations. So why not just keep increasing testosterone levels in these males? Well, there's the idea that there is some balance here, that they get more mates with higher testosterone, but it might have a negative side effect. And in this case, it's hypothesized, or the research question is about whether or not it causes an immune reaction in these birds, so that they start having increased or heightened immune that may compromise them to other sorts of diseases. So what they did was they measured antibody production in these male red-winged blackbirds under high testosterone levels. So they had 13 male birds. They measured antibody production in these 13 males. Then they tweaked, right? They did a little tweak, so it's an experimental design, manipulative. They implanted a tube filled with testosterone that dripped into the bird's bloodstream. And then they let that happen for some amount of time, and they measured antibody production again. Under sort of their research question, we're going to assume that if testosterone has a negative side effect on the immune system, antibody production should go up after testosterone is given to these male birds. Here's the data. Okay, so we have the male ID, so 1, 4, 5, 6, those all indicate a single experimental unit. They measured antibody production before and after. And if we look at the means in antibody production between before and after, that doesn't look like a whole lot of difference. The other thing we might notice is that these birds didn't all start at the same antibody production before. And that is a problem for us, and why we also need to use a paired design. These observations aren't independent. So the individuals varied in their baseline antibody production levels and probably also their testosterone levels. And because of that, it could obscure any effect of the additional testosterone. On this graph where we see antibody production before and after, we can see that these dots fall mainly on a line. And we're going to see that that kind of relationship between two variables means that they're not independent. It means that we could have a problem with dependence here. And again, reason to use the paired design. So what do? Instead of taking these before and afters and comparing them directly, we take a difference. So just as I said, we'll take the mean of the value of an experimental unit before, we'll minus the after, and we'll get the difference. And it is that data in the difference column that becomes the data we use in our statistical null hypothesis test. And here's our frequency distribution of those differences. And we want to now test this against 0 with the paired sample t-test. Notice our sample frequency distribution is centered on 0. So let's state our hypotheses. Our null is that our mean difference between the before and after equals 0, and our alternative is that it doesn't equal 0. So we're going to calculate the mean of the differences, and there it is, negative 0.056. The mu null is hypothetical difference 0. And the standard error of the difference is 0.044. We plug that into our t calculation, and there's our test statistic. Our test statistic is negative 1.27. And now, just like we wanted to know on a one sample t-test, we want to know if this exceeds a critical value and what is the probability associated with that. So now we're going to take that T test statistic that we got and look at the T sampling distribution where n equals 13, thus degrees of freedom equals 12. And remember, there's a bunch of different T theoretical sampling distributions, all based on our degrees of freedom. And so with that distribution, we see that a critical value is plus or minus 2.18, and that's at our alpha of 0.05. So those red regions represent the 5% area above 2.18 and above negative 2.18. And we see that the T value we got of negative 1.27 does not exceed this critical value, and it is in the retention region, remember? So the red is the rejection region where we reject the null, and the uncolored region is the retention region, and that's where we retain or fail to reject the null. So we have that piece of information. It comes with a probability for our test statistic. So the probability for our test statistic is 0.23, and that's a high, way above 0.05. So we have what I call a low T, a high P, and thus we're going to fail to reject our null. We can look at the 95% confidence interval for the difference as well, and that can be calculated as you take that mean difference, and it's plus or minus our T critical value, 2.18, times our standard error of the difference, which we already calculated, and we can see the lower is negative 0.152, and our upper is 0.040. This crosses 0. So again, this tells us that we cannot eliminate that as a possible difference in the population. And so thus, we're again going to fail to reject our null. So, failed to reject. So our evidence suggests that elevating testosterone did not change antibody production in these birds. So my final question, and I'll ask this in class, does this mean the null hypothesis is true?